good morning and a warm welcome to all to a new session of ASAP online classes. Today, we will learn about support vector machines, which comes under data warehousing and mining of Module 4, Semester 6 of Information Technology Engineering. The session will be handled by Mr. 𝐒𝐮𝐩𝐸𝐽𝐸𝐽𝐸𝐸 M, Assistant Professor of Department of Computer Science and Engineering, LBS College of Engineering, Kasaragod. We welcome you, sir. So we are now moving on to our session. Over to you, sir.
Okay. Good morning, all. Today's topic is support vector machines. Support vector machines is a supervised learning technique. When I say supervised, means we have labels to do the training. You can take an example. You consider a set of n observations. Say you have m features. You are labeling these features with positive or negative, or yes or no. Now you can use this entire data set to train your model. Usually, when we do the training, we will divide the entire data set into training set and testing set. We will train the model using the training set. Once you complete the training, you can measure the performance of a model using the test set. Say you got a new data, an unseen data. You can use your model to predict the label. So such kind of learning, we call it as supervised learning. You can think about as a very simple example. Consider all the students in a class. You collect the features, for example, height of a student and hair length of a student. Using that, you can actually predict whether it is a boy or a girl. That's a simple example of how this supervised learning works. Today, we are going to discuss the original SVM. It's a sophisticated algorithm developed by Wapnick and Alexey. So let us look into that. You consider this vector space. Here you can see there are features. These features are labeled with positive and these features are labeled with negative. So the entire vector space consists of positive samples, 2 positive samples and 2 negative samples. Usually in our data set we have 1000, 2000 or more than that. Okay, but for the sake of simplicity, we will be considering a few samples here. Now, what is our aim? Our aim is to divide the vector space with a decision boundary. So how you will divide this vector space with a decision boundary? Now, why you are going to divide this vector space with a decision boundary? Say you are going to divide this vector space with a decision boundary like this. Now, when you get a new data, say I'm going to represent it like this. Okay, I got a new data. So the decision boundary will help me to classify the unseen data to positive samples or the negative samples based on the decision boundary. You can compare this decision boundary with the decision boundary of other algorithms as well. Now, how to divide this decision boundary using support vector machines? Here, we need to divide these positive samples from the negative samples. I can draw a straight line like this. This straight line is very close to the negative sample. Or I can draw another straight line like this. This straight line is very close to the positive samples. Or maybe another line, the median line. But the question is, which straight line you will choose? You can have more straight lines. You can draw a line like this. Okay, you can have infinite straight lines that can be drawn to separate this positive from the negative samples. Which line you will choose as decision boundary? Let us see the decision boundary of a support vector machine. In support vector machine, the decision boundary is drawn with the view of putting the widest street. You can think this as a street. Okay, and this is the median line of the street. Okay, so you can think it as a street, the widest street that separates these positive samples from the negative samples. This actually makes support vector machine differ from all other algorithms that you have learned so far. It is about the widest street that separates the positive samples from the negative sample. Now, the question is how you can write a decision rule that will use this decision boundary. Let us see how we can write a decision rule for this decision boundary. For that, you imagine a vector W of any length. There is a constraint here. When you draw this vector, this is a vector W. When you draw this vector, that should be perpendicular to the median line. So this is the median line of the street. Okay, and when you draw this vector, it should be perpendicular to the median line. That is the only constraint here. We don't know anything about the length of the vector. Okay, there's no idea. Now you consider another point U somewhere around here. Okay, I need to classify whether U belongs to positive samples or negative. Okay, so I'm going to make it as a vector U. So we need to find out whether it is in the left side of the street. So this is the left side of the street, or it is in the right side of the street. For that, what I'm going to do is I'm going to take the projection. I'm going to project this U to the vector that is perpendicular to the street. Okay, perpendicular to the median line. I'm going to take a projection of U on W. When I do that, it will give you the distance in this direction. Okay, when I'm going to take the projection of U on W, that will give me the distance in this direction. So once you get the distance in this direction, then you will come to know that particular sample U belongs to the left side or the right side. Okay, you will be able to tell which side of the street U is. Okay, now let's write a decision rule based on this assumption. So I'm going to write the projection as U dot W That is a projection of U on W. Okay, U dot W greater than or equal to some constant, say C. That C shows the length. Okay, I'm taking that length of the vector W to the other side. Okay, I am making it as a constant. So if the length is greater than or equal to some constant, then I can say that it is a positive sample. The dot product of U and W will give you the projection of U on W. Okay, and I'm making a constant over here for the length of W. If that value is greater than or is equal to C, then it is positive sample somewhere around here. Okay, so for sake of simplicity, I'm putting C is equal to minus B, and I'm going to rewrite our equation. Now the equation will be like this: dot product of W dot U plus B greater than or is equal to 0. I'm taking minus B to the other side of the equation. So the equation will be now dot product of W dot U plus B greater than or is equal to 0. Then it is positive. We have no idea which constraint B to use here. There is no idea about your W either. The only constraint here is that the W should be perpendicular to the median line. That is the only constraint we have here. See, there are a lot of W that is perpendicular to the median line. It can be of any length. Okay. Now let us see how we can add some more constraints to this decision rule and get something out of it. Okay. For that, say I'm going to take the positive samples and the negative samples separately into our decision rule. So I will label the positive samples with X plus, okay, and the negative samples with X minus. So I will rewrite my decision rule like this: W dot X plus B greater than or is equal to 1. Okay, so it's a positive samples. So that means the decision rule will give you a value which is greater than 1 or okay or 1, whatever it is. Now what about the negative samples? If the sample is negative, the decision rule will give you value minus 1 or lesser. You can be anywhere in the street, okay, greater than or less than 0. But if you are on the right side of the street, okay, the decision rule will give you value greater than or is equal to 1. Or if you are in the left side of the street, here you'll be getting value minus 1 or less than minus 1. Okay. That is the two decision rules that we have now. Now I am going to introduce a new variable, y. For the positive samples, the value of y is 1. And for the negative samples, the value of y is minus 1. So you'll be thinking, why I am introducing a new variable? It's just for the mathematical convenience. Now I'll multiply this with the equations respectively. So when I multiply yi is equal to 1 for the positive samples with equation 1, I'll be getting yi into w dot xi plus b greater than or is equal to 1. Now I will do the same for the negative samples. When I multiply yi is equal to minus 1, so what will happen? When you multiply an inequality with minus sign, inequality changes. So less than is equal to will become greater than is equal to. Okay, and minus minus will become plus over here. So the equation will become yi into w dot xi plus b greater than or is equal to 1. Look at these two equations now. Are they same? Yes, they are the same. Now you have a single equation with you. So I'm taking that one to the left side and just rewriting my equation. So it will be yi into w dot xi plus b minus 1 greater than or is equal to 0. I'm just rewriting the equation. Now, if the value of this constraint is equal to 0, that means the vectors is in this getters. Okay, these getters. Later we will come to know that they are your support vectors. So this is a constraint we have now. So let us move to the next slide. So you have a constraint now. Okay, so what is the aim? We need to find the width of the street. As we say, the width of the street is this, right? This is the width of the street. So this street separates its positive samples from the negative samples. Now to find out the width of the street, I'm going to take a new vector. Okay. I'm going to connect that to the positive sample. So this vector x plus connects to a positive sample. I'm going to take another vector. This vector is to a negative sample. So now you have two vectors, one to the positive sample and the other vector to the negative sample. Now let's take the difference of these two vectors. Okay, difference of this positive vector and the negative vector. So you will be getting a vector like this: x plus minus x minus. This is the difference between these two vectors. Now you consider a unit normal in this direction. A unit normal in this direction. So this normal should be to the, it should be the perpendicular. Okay, perpendicular to the median line. Now what I'm going to do? I need to know the width of the street. So what you can do? You can take the projection of this difference vector. Okay, this is the difference vector you have. Take the projection of this difference vector to the unit vector. When you do that, you will be getting the width of the street. So to take the projection, I will take the dot product of this vector with the unit vector. Now I will write the equation. So now your width of the street is x plus minus x minus. So that is the difference vector you have. You take the dot product with the unit vector w by the norm. So you will represent unit vector like that. The vector divided by its norm. So you got the width now. So the width is a scalar quantity. You got the width of the street now. How you got that? We take the projection of this difference vector to the unit vector to get the width of the street. Okay, we already have a constraint. So this is our constraint, right? Now you consider the positive samples cases. So we already know that for positive samples, this yi is equal to 1, and for negative samples, this yi is equal to minus 1. So to get something out of this, I'm going to substitute yi is equal to 1 for the positive samples and yi is equal to -1 for the negative samples. So when I substitute yi is equal to 1 for the positive samples in this equation, I'll be getting 1 dot. Here you can see this is the constraint. I'm multiplying it 1 -1 is equal to 0. Now you will be getting this expression, dot product of w dot xi is equal to 1 minus b. So this is for positive samples. Okay. Now let us do it for the negative samples. When I do it for the negative samples, I'll multiply it with -1. So you multiply with -1 over here, you'll be getting w dot xi. You can take w dot xi to the other side. Okay, so you'll be getting -1. You multiply -1 with b, minus b. So the expression will become w dot xi is equal to -1 minus b. So we have now two values corresponding to positive samples, that is 1 minus b and -1 minus b. So what you can do is, you see this expression, the width. So indeed it is a dot product of this difference factor with w. So you can actually replace this dot product of x with w with 1 minus b for the positive cases, and you can here multiply x minus into w with -1 minus b. So when I substitute, I'll be getting like this: 1 minus b minus 1 minus b. Okay, I have taken the dot product. I have replaced this dot product with 1 minus b, and there's the -1 minus sign over here. So this b will become plus b. So I'll just cancel it out. Now the width of the street is 2 by the norm of w. How I got this? I got this by substituting the value of y in the constraint. Okay, and using that in the expression of our width. So now the width of the street is 2 divided by the norm. Okay, what is our aim? We have to find the maximum width of the street. We have to maximize this width. Okay, so that is the aim of today's presentation. We have to maximize width of the street. I think we need a little more time for this theory session. So maybe we'll take 35 minutes. Okay. So to maximize width of the street, I'm going to write the expression. So we have to maximize this value, that is 2 divided by the norm. We have to maximize this term. So 2 is just a constant, so I'm dropping that. So I have to maximize 1 by the norm. It is same as minimizing this norm, which is same as minimizing half of the norm, and you square the norm. Okay, why I'm going to do this? Again, it is just for mathematical convenience. Later, when we take the derivative and all, no, this 2 and all will get cancelled, and we actually need the norm square to match it with the dot product. So that is just for the mathematical convenience later. Okay, so now you got an expression to be minimized. So this is the expression that you are going to minimize. Okay, so that you will have maximum width for your street. This is the expression. Now you have a constraint. You have an expression now, and also you have a constraint. So now it is an optimization problem. How you are going to solve this optimization problem? There are various techniques, but today we are going to use Lagrange multipliers to solve this problem. It is because when you go for other methods, it will become more complex when you deal with nonlinear data. And what is our aim? The aim of this Lagrange multipliers is, say, you have to find an extreme of a function. Don't bother whether it's a maximum or minimum. So you have to find extreme of a function with a constraint. It will give us a new expression which can be either minimized or maximized without thinking about the constraints anymore. So once we get our final results, you'll come to know that we just need to take the dot products of the feature vectors or support vectors. For that, we are going to use Lagrange multipliers here. Let us formulate the Lagrange multipliers now. So we already have our expression to minimize, and we already have our constraint over here. So I'm going to write the Lagrange over here. So this is the term that you have to minimize. You have to minimize half of the norm square. And I'm writing the constraint over here. You multiply the constraint with a Lagrange multiplier. So this is the Lagrange variable here, alpha I. So the summation will add all the constraints. Okay, the summation function will add all the constraints by multiplying it with the Lagrange multiplier alpha I. So this is our expression now. This term we have to minimize. Okay, we have kept our constraint over here. A little bit of mathematics now. We need to take the partial derivative of this L with respect to W. So when I take the partial derivative, you know that here we have taken the norm square. Okay, see, this norm square is nothing but the dot product of W with itself. So you can think, when you take a dot product of W with itself, okay, you are actually getting norm square. Then you can apply that differentiation. Okay, derivative of L with respect to W. So you are taking W dot W. So it will be 1 dot W plus W dot 1. In turn, that will give you 2W. Okay. So the 2 and this 2 will get cancelled. So in turn, you will be getting a W over here. So this part you have W. Now look at this constraint now. When you take partial derivative with respect to W, here you can see you have term over alpha I here, there is a yi over here. This term will become 1. So you have alpha I, yi, xi. What about this term? Alpha I, yi, b. So they are all constants. So that will be 0. There is no W term there. Then again, alpha I minus 1. So that term is also 0. So now you got an expression like this. So I'm writing in this form. Now your W is the summation of alpha I, yi, Xi. What is that? It is the linear sum of all the samples multiplied with the Lagrange multiplier and the labels. So you have done a lot of mathematics here. Okay, but what you got now? W is the linear sum of, I cannot say it's all samples because alpha I will be 0 for the samples other than your support vectors. Okay, so I'll say W is the linear sum of some samples. So for support vectors, alpha I is non-zero and alpha I is 0 for all other samples. I'm going to take the partial derivative of L with respect to B. When I take partial derivative, this term will become 0. Okay. Minus alpha I yi wxi, this term will also be 0. Minus alpha I yi, you'll be into the derivative. So you'll be getting minus alpha I yi. And the last term will also be 0. So you'll be getting minus alpha I yi is equal to 0. So this is the condition you got now. So now you got an expression like this. Okay, the way the W, and you also got a condition like this. Now let us summarize it. Okay, let's summarize that. So this is the Lagrange you have. I got W and I got an expression like this. Now I'm going to substitute this W into this expression. I'm going to substitute this W into this expression. Okay. When I substitute that, see here I will write it as dot product of two feature vectors. Xi is one feature vector, Xj is another feature vectors. Okay. Minus alpha I. Here also I substitute the value of W. So just simple algebraic. Okay. So I'm just substituting it. Now, what is happening here? I'm just multiplying alpha I, yi, and this xi. Okay, in turn, it is a dot product. Dot product of alpha j, yj, and sj. Minus alpha I, yi, and b. And there's a minus over here. So minus alpha I into minus 1. So plus alpha I. This term, we already know that it is 0. Okay. Now when I rewrite it, I will take this alpha I at the beginning. So L is equal to alpha I plus 1 by 2 into the same expression. Okay. Dot product minus the dot product of these samples. I'm just taking it as double summation. Okay, I will take this alpha I, yi, alpha j, yj outside and writing it as dot product of xi dot sj. So rewriting is Lagrangian by taking as a double summation. So this is our final Lagrangian expression. So we have done a lot of mathematics, and what we got now? This shows that the optimization now depends only on the dot product of the pairs of the samples. We have done a lot of mathematics here, and the final result, it shows that it is just dot product of sample. So this is the final Lagrangian equation that we got now. Okay. Now let us look at the decision rule. I got a new sample. I need to classify this sample. I need to find the label. What you can do, you take the dot product of the support vectors with U. It will tell you whether it is a positive or the negative. That means the decision rule now depends only on the support vectors dot product with the unknown. See, unlike in many other algorithms, you don't require the entire training sample, okay, to make the prediction. So that will make the predictions of support vector machine much faster than other algorithms, as well as the computation is very less, because we don't read any complex operations. We just need to take the dot product only. Okay, so that's the decision rule we have. Now we can move on to the QA session. Then we'll move on to the algorithm and the problem part.
Okay, sir. Okay. Sir, I think this is a basic questions on നമുക്ക് വന്നിട്ടില്ല sir.
Okay.
Is support vector machining is a linear classifier?
Yeah. Support vector machine, the support vector machine that we are going to discuss now is a linear support vector machine. Okay. But you can also solve non-linear problems using support vector machine. In the real life data that we used to get now may not be linearly separable. Okay, I'll just show you a simple example. Say you have negative samples like this, you have positive samples like this. Okay, so in the example that we are seeing now, okay, this is your decision boundary and these samples are linearly separable. But the real time data may have some noise. Maybe you get some sample, positive sample over here. Then you cannot actually use the decision rule that we have defined now. For that, we have another different variation of support vector machine. It's called the soft margin. That is actually the topic of next section. And also regarding the non-linearity, say you consider another scenario. I'll take another example. Okay. So you can see there are some positive samples over here. Okay, there will be some negative samples. So in this case, there is no way you can actually separate these positive samples from the negative samples with a linear SVM. For that, you have to do a kernel trick. So that is also the topic of next session. So that kernel trick will transform your original feature vectors into another dimension. You can think something like this is a 2D data. Okay, you have x and y axis. You are changing that to a 3D. Okay, using a kernel transformation. You can use a linear kernel or there are many other kernels. So when you transform that, maybe this positive will have more weights in the z direction and these negative values will be having less weight or vice versa. So that you can actually separate this positive from the non-positive. So that is the case of the data which is not linearly separable. Okay, so for that we have to use kernel tricks. So that means you can also deal with non-linear data for support vector machine. Okay, we will study in detail when we discuss kernel tricks. Hope it is clear.
Sir, hello.
Yeah.
Thank you, sir. Sir, one question കൂടെ ഉണ്ട്. What are the disadvantages of XVM?
What are the disadvantages of XVM?
അതെ sir, അതെ.
See, it's a bit of a history. See, the SVM, it was developed in 1960s. And at that time, see, the author, Mapnik, he published it, he tried to publish his papers and most of them got rejected. Because at that time, this SVM, it cannot handle this non-linearity problems. And in recently, there's this kernel tricks and all was introduced. Okay, and SVM was able to solve all the non-linear problems, especially in dealing with that digit and return digit classifications. So SVM has become much popular in dealing with this handwritten digit classification. Now, you think about a neural network. So a neural network, it has also got a kind of history. So the simple spectrum models, it cannot actually solve nonlinear problems. There we have multi-layer spectrum models. And the support vector machine now has been surpassed by the deep neural network. The main reason is because support vector machine is built to deal with binary classification. It can also do multi-classification, but the core of support vector machine is dealing with the binary classifications. And you cannot actually use support vector machine directly to a multi classification. That you can say some of the disadvantage. Also, when I say about disadvantage, okay, see, the support vector doesn't deal with any probability. Okay, all other models deal with, they are probabilistic models. Support vector machine is based on the support vectors. Okay, so these are the support vectors. Okay, so in that sense, the support vector machine was very efficient compared to other algorithms. Okay, and when you compare it with the deep neural networks, now you have enough computation power to deal with all the the iterations in deep neural networks, the complex network that you can form. That's why now deep neural network is actually try to be better for certain problems than support vector machine. So you cannot say that there is a straightforward disadvantage for support vector machine, but the deep neural networks overcome some of its limitation, and now more research work is actually going in deep neural network. Hope that question is clear.
Okay, sir. So, a question would enter. Can we use SVM in unsupervised learning?
Yes, you can also use SVM in unsupervised learning. There is support vector clustering also. It has been proposed by some of the authors. But it is currently it's a research topic only. Okay, the original SVM that has been developed is basically used for classification only. But you can use support vector machine for unsupervised also.
Okay, sir. I hope that we are done with the questions. You can continue the session, sir.
Okay, so let us move to the algorithm now, and we will do a simple binary classification problem. Now let us summarize that. So the SVM classifier. So what we have done is we have started with a minimization problem, the original problem. Now we have used Lagrange multiplier, okay, and we change that into a dual problem. Here you can see the dual problem is we have to find a vector alpha which maximizes this equation, okay, subject to the conditions. This is the condition. So as I said, this problem can be solved by many other methods also. But why you are insisting with Lagrange multipliers? The reason is because you can see you have to just take the dot product of two samples. So this will be more useful when we actually go for higher dimension, especially when you have problems which is not linearly separable. Okay, as I said, when you deal with problems which is not linearly separable, you go into higher dimension. So in higher dimension also, you need to just take the dot product of samples. Okay. Now I am going to write the equations of W and B. So the W we already know, it is the summation of alpha, Ya, and Xi. The solution of B is beyond scope of today's discussion, but it is very simple. There are many methods to solve B also. So here, what we are going to do, For the positive samples, you take the dot product of W with the feature Xi, and you take the minimum out of that. Okay, you have many features. With positive labels, you take the minimum value. Here, you take the dot product of W with Xi for the negative samples and take the maximum out of that, and take the average. So that will give you B. You can compute W and B in that. Then you can write the final SVM classifier function like this: f of x is equal to W dot x minus B. So that is the SVM classifier. So what we are going to do? We are going to find a vector alpha which maximizes this. Okay, subject to this condition. And you can compute W and B with this equation, and finally you can write the classifier function like this. So let us do a problem. Okay, so this is the sample data set you have. So for simplicity, today we will consider only two samples. There are sample 1 and sample 2. These are the two features, and the features have class labels +1 and -1. Okay, so what is our aim? We have to find a vector alpha which maximizes this. Okay, subject to the condition. So let us write the values. So how many samples you have? You have two samples. So the sum function now will be I is equal to 1 to 2. And here the double summation, it will be I is equal to 1 to 2 and j is equal to 1 to 2. Okay. Now the feature vector, so I will write it as x1 is 2, 1. And feature vector x2 is 4, 3. Okay. Now y1 is positive 1 and y2 is negative 1. And your alpha, you have only two samples over here. Okay, so we know that the Lagrangians depends on the number of samples. Okay, so here you have you do it as alpha 1 and alpha 2. So when I substitute these values into this expression, okay, so here this term is sum of alpha I, so that will become alpha 1 plus alpha 2. Okay, alpha 1 plus alpha 2 minus 1 by 2 into, here it's a double summation. Okay, so alpha 1, y1, y1, x1, x1. Okay, for I is equal to 1, j is equal to 1. So you will get this term. Now for I is equal to 1, j is equal to 2, you will be getting alpha 1, alpha 2, y1, y2, x1 dot x2 dot product. Plus now I is equal to 2, j is equal to 1, alpha 2, alpha 1, y2, y1, and the dot product. And for 2, 2, alpha 2, alpha 2, y2, y2, x2, x2. Okay, I just substituted these values in the expression. Okay, now I'm going to put the values of this y1, and I'm going to take the dot product of x1 dot x1, x1 dot x2, x2 dot x1, and s2 dot x2. Okay, when I take the dot product, so here this term will be +1 +1 for y1. Okay, so taking dot product of x1 with itself, so it is 2 into 2 plus 1 into 1. Now dot product of x1 with x2, 2 into 4 plus 1 into 3. Dot product of x2 with x1, 4 into 2 plus 3 into 1. Then dot product of x2 with x2, 4 into 4 plus 3 into 3. Okay, when I simplify it, okay, I'll be getting alpha 1 plus alpha 2 minus 1 by 2 into alpha 1 square minus 22 alpha 1 alpha 2 plus 25 alpha 2 square. So that this expression, okay, you have alpha 1 plus alpha 2 minus 1 by 2, 5 alpha 1 square minus 22 alpha 1 alpha 2 plus 25 alpha 2 square. So we have to find a vector alpha which maximizes this expression. This is the expression now to be maximized. Okay. Now let us substitute to this condition now. Okay. So you put alpha 1 y1, okay, it's a summation, plus alpha 2 y2 is equal to 0. Okay. Now you put the value of y1 to plus 1 and y2 to minus 1. So the expression will become alpha 1 minus alpha 2 equal to 0. That is the two expression that we have got. So I'm just rewriting it. So you have to find now the values of alpha 1 and alpha 2 which maximize this expression. Okay, so the conditions is alpha 1 minus alpha 2 is equal to 0. And why alpha 1 greater than 0, alpha 2 greater than 0? Because here we will only consider the case of support vectors. Okay, we don't bother anything about the other alpha. Okay, we need only support vectors. So this is a expression you have, and this is a condition. Okay. Now you are going to substitute these two in 1. So the conditions, okay, alpha 1 minus alpha 2 is equal to 0. That means alpha 1 is equal to alpha 2. Right. So I'm going to substitute that in the equation. So I'm substituting in 1. When I do that, okay, so this is the expression you have phi of alpha, where you have to maximize alpha 1 and alpha 2. When I substitute, this term will become 2 alpha 1 minus 1 by 2 into 8 alpha 1 square. So this will become 22 alpha 1 square. Okay, minus 25 plus 5, 30 minus 22 alpha 1 square. So that will be 8 alpha 1 square. So your phi of alpha is 2 alpha 1 minus 1 by 2 alpha 1 square. Now we have to find the maximum. Okay, so for phi of alpha to be maximum, you have to take the derivative and you equate that to 0. The derivative is very simple here. You take the derivative of this function with respect to alpha 1. When you do that, here you will be getting 2 minus this term. Okay, is alpha 1 square. So the 2 and this 2 will get cancelled. You will be getting 8 alpha 1. So 2 minus 8 alpha 1 is equal to 0. So alpha 1 is 1 by 4. Now you can substitute this alpha 1. So the alpha 1 is 1 by 4. You can substitute that in this equation and you will get alpha 2 is also 1 by 4. Okay. So you can also take the derivative, second derivative, but when you take the second derivative, this value, okay, this take the second derivative of this, so it will be negative. So that means this is the maximum. Okay, so this is the maximum value that you have. So now you got the maximum of the function. Okay, so yeah, you got the values of alpha 1, alpha 2, where this function is maximum. Now what is the next step? We have to find out the value of W and B. Okay, so let us go to the computation of W and B. Now you know that the expression of W is alpha I, Ya, Xi. So it's direct substitution. Okay, so you put alpha 1, y1, x1 plus alpha 2, y2, x2. Okay, so we are going to substitute the feature vector values to compute your W. So we already have what? Alpha 1 and alpha 2. Okay, we also have all other values. So it's a direct substitution only. We substitute 1 by 4 into plus 1, y1 is plus 1, okay, and y2 is minus 1. And it's a vector. This x1 is a vector, s2 is a vector. So it will be a simple vector addition. Okay. So you'll be getting 1 by 4. Okay. So this term multiply to you're multiplying plus 1 to this vector, it will be going to 1. You multiply minus 1 to this vector, it will become minus 4 minus 3. I'll take 1 by 4 outside. Now you can just add these two vectors. When you add these two vectors, okay, you'll be getting 1 by 4 into minus 2 minus 2. Now, when dividing by 1 by 4, you'll be getting minus 1 by 2 minus 1 by 2. So that is the value of your W. Now you have to compute the value of B. So we already have this equation for computing value of B, but see, it is minimum and maximum when you have more number of positive and negative samples. But in this case, we have only one positive, only one negative. So we are not going to use the minimum and maximum over here. Okay. So what you have to do, you have to just take the dot product of W with positive sample, dot product of W with the negative sample. Say if you have one more sample over here, say 3 positive, then you have to take the minimum in this case. Okay. So here it's a direct substitution. 1 by 2 into, here the W is minus 1 by 2, okay, minus 1 by 2. So you are taking dot product of this W with x1. So minus 1 by 2 into 2, minus 1 by 2 into 1. Now take the dot product of W with the second sample. So minus 1 by 2 to 4, minus 1 by 2 into 3. Okay, so that is equal. You are just doing the addition, and here you'll be getting, see, this term is minus 3 by 2. Okay, and this term is minus 7 by 2. Okay, minus 3 by 2 and minus 7 by 2. So it is minus 10 by 2. Okay, so you multiply, you divide by 2, so you'll be getting minus 5 by 2. So that is the value of B. So using this expression, you have calculated W and you have also calculated B. Okay. Now you have to write the final classifier. So the classifier function. So you have the data set now. Okay. Now you are going to write the final classifier function. So this is our positive sample. Okay. It is 2, 1, and this is our negative sample. So now you need the decision boundary. Okay. It should be something like this. Okay. So the classifier function is f of x is equal to w dot x minus b. So we already have the vector w. We also have the vector x. Okay. So time being, we use this x as x1 and x2 because it is your model now. Okay. Minus b. So I'm substituting the values of w and b to this equation. It will be minus 1 by 2, comma minus 1 by 2, and you're taking the dot product of w with x1, x2. And the value of b is minus 5 by 2, so it will become plus over here, plus 5 by 2. So minus 1 by 2, x1, minus 1 by 2, x2, plus 5 by 2. So it will be minus 1 by 2 into x1 plus x2 minus 5. You can rewrite that as the equation of the margin, the line. Okay, I'm just rewriting. When I rewrite that and equal to 0, you will be getting the equation. x1 plus x2 is equal to 5. Okay. So that means what? Here, if you put value of x1 to 0, okay, the x2 will be 5. You put value of x2 to 0, the x1 will be 5. So you'll be getting a line like this. That is the final equation you have. Okay. So any doubt?
Sir, there is one question. Sir, how we are selecting the best fit line from many lines that gives maximum margin?
Please say it once again.
Sir, how we are selecting the best fit line
Yeah.
from many lines that gives maximum margin?
Yeah, for that only we are actually doing the optimization. Okay, so we have done the optimization problem. Okay, when you go back to this particular maximum width equation. Okay, so I think I have to. Okay, so we are actually getting by solving this maximum width equation. We are going to find the optimal line by maximizing the width of the street, and your line is nothing but the median. Okay, see, it's actually you can consider that as equation of a plane when you deal with higher dimension. So this is the maximum margin plane that you have, which separates the positive from the negative. And you can see over here, this is the support vectors you have. Okay, so this is the support vector, and this is also a support vector. So this is the maximum margin plane you have, which separates positive and the negative cases. And you are actually building that maximum margin plane by using these support vectors. These are our alpha, and you have weights for your alpha also. Okay, so I'll just draw it. See, here you have two positive samples. Okay, as support vectors. You have only two negative samples as support vectors. You have only one positive samples as support vectors. So your weight will be something like this. So this is your two negative samples. Okay, and this is your positive sample. So these are the weights of your alpha, the Lagrange. Okay, and you are solving the optimization problem to get that maximum width.
So, sir, I think for now we are done with the questions, and we hope that more questions will come in the coming sessions also.
Oh, sure, sure.
And so, sir, that was a wonderful session and well explaining too. And we hope that the session was helpful to all of you. So, thank you so much, sir, and to all of our attendees for taking this time to attend our session. Thank you so much.
Okay, thank you all.